Okay, so we'll resume the class. So now, as we talked before, so we said matrix is a function, and when we're talking about function, we have to know that what is mapping. So what space is mapping from to mapping to? And we're going to talk about that space a bit because we need to know about some of these properties in order to know more about this overall linear algebra and their basic concepts. And that's going to be vector spaces. So, like how we talked about real numbers as our basis for understanding analysis, there's also a similar concept in linear algebra, and that is called vector space. So it's not that different. Just think of it like a real number system, basically. So as real number system was our main playground for analysis, the vector space is going to be our main playground for linear algebra. So it's not that difficult concept. It's just like similar concept of a real number system, except it has some different qualities. Remember I told you about, like, when we talked about field analysis, we're going to be talking more about it in detail. And here it comes out, because in vector space and in algebra, we first need to know about the overall quality and characteristic of a field in order to talk about vector space. So before we start learning about a vector space, we first need to know about what field does. So what field is nothing difficult. What field is basically when you have a set, we're just putting some sort of structure or property onto the set. And if the set has this structure, we call that set to be a field. So what is a field? It has very nice structure. For example, so let's assume that F is some non-empty set, and there are some binary operation called addition and multiplication, which what it means is basically like this. So for addition, you can add two element in F, and their addition is going to be still in F. So like, for example, for real numbers is a field because if you add 1 and 2, you get 3, and 1 and 2 are all on R, right? And 3 is also on R. So what this means is that if you add elements inside F, the addition is going to still stay inside the element. And this is also very interesting quality because there are some cases where if you add or subtract some stuff, it's not going to stay inside. For example, like if you, if you're thinking only about natural numbers, and maybe you did subtraction, for example, and you get like -3 or something. 1 and 4 are all inside natural number, but -3 is not a natural number, right? In this case, it's kind of hard to say that this is has a field quality. And sometimes we call this, in other terms, we call this property as being closed. In Korean, it's called 닫혀있다. So 들어보실지 모르겠지만 가끔 뭐에 닫혀있다, 더하기에 닫혀있다 이런 말 있잖아요. 그게 무슨 말이냐면 결국에는 if you add something, if it stays still inside that set, so it's one of the elements, then we call that to be closed. So that's what we say it. And similar with the multiplication. So basically, if you multiply two elements in the field, I didn't say it's field yet, but if you multiply two elements A and B inside F, and if the multiplication product still is an element of F, we say that there's a multiplication operation there. So for now, on a non-empty set F, we define two operations, addition and multiplication. So these two, multiplication and addition, works perfectly in the set. And we assume that. And if F satisfies other following conditions, we say that F is a field. And here are the lists from 1 to 6. So if F has an operation addition and multiplication, and if this set satisfies following conditions, we call this set to be a field. Okay? So basically what this means though, is just means that the field adds up very well, has very nice qualities that we want it to have. So first one is, well, associativity of addition and multiplication. We saw this already because what this means is that for three elements A, B, and C, even if you add from B, C first, or if you add from A, B first, the value is going to be the same. If that holds, we say the associativity condition holds. And also for multiplication, similarly, if you multiply from BC first, AB first, if you still get the same values, then we also say that the associativity of multiplication holds. So very nice quality. And also, the commutativity of addition and multiplication also has to hold. So even if you switch the operation of addition and multiplication, you have to get the same values. That's also very nice quality. And the third one might be a bit new to you, which is additive and multiplicative identity. There has to be two distinct elements, 0 and 1, inside the set F, such that if you add 0, you're just going to get the original element. And if you multiply some element in F with 1, you're going to get the element itself. So what this means is that, remember, like, in Korean, I think it's like 항등이었나? 뭐 그런 표현이 있을 거예요. 그러니까 뭐 항등원인가? 항등원 뭐 맞나요? 항등원이라고 하는데 이제 if you have any kind of element in field, so what 0 mean when you say it's additive identity? If you add 0, it's gonna get just A, and this holds for any kind of elements. The 0 basically just gives you the origin element, right? And similar with multiplication, we say 1 is a multiplicative identity because it has this quality. If you multiply it, you still get the former element, right? So we call this additive identity and multiplicative identity. And sometimes in some sets, they don't exist. So if this F is a set where additive identity and multiplicative identity exist, that also is one of the conditions for a set being a field, okay? Again, last three conditions. So it's additive inverses. So for every element A in some F set, there's some element denoted minus A, which is the additive inverse, such that we add two elements together, we get the additive identity. So what does this mean? So in Korean also, I think this means 여건. 그래서 any element, there's like an element called minus A. So you add them up, you get 0, right? Which is the additive identity. So if there's such element for every element, then it also shows that this set could be a field, okay? Because there are some sets with which there's no such properties. And also similar to the additive inverses, there's multiplicative inverses, so which is 1 over 4, right? This gives you 1, which is the multiplicative inverses. So if these two exist, the condition also holds. And the last quality is the distribution of multiplication over addition. So like that. So you multiply A to B plus C, and what you get is A times B plus A times C. So basically you're distributing the multiplication to B and C, right? So that has to also hold. And to summarize, if there's a non-empty set F where addition and multiplication is defined and is closed, and if 1 to 6 conditions hold for this set, we call this set to be a field. So that's actually like the rigorous definition of a set being a field. So when we said in the past, when we said like real numbers are a field, we actually mean this. So basically it holds. Very nice properties. Okay, so some example of field. Obviously, rational numbers, real numbers, they're all field. So in summary, it's kind of safe to assume that many of the number system we use in economics is field, which means basically it's just a good number system. And sometimes we denote element of a field scalar, or more Greekish pronunciation scala. So for element in a field, we call them scalar, right? Okay. And you might hear this term sometimes, but don't be scared by it. It's nothing. It just means it's just element of a field. Okay. So then we call that scalar. All right. So we talked about field when we actually want to know about vector space. So why we talk about field? Because we need to know the definition of field if we want to define a vector space. And you can kind of see from the definition of vector space, we have to define field first, right? we say that some set V, which is non-empty, is a vector space over a field F. Okay? So like exact definition of a vector space is actually not just some set, it's actually a set V, non-empty set V with some field, right? So field can change actually. So vector space over field F is a non-empty set V, also with two binary operations, right? And it also has to satisfy 8 axioms listed below. So it's kind of similar to the field because remember that the field we had to define addition and multiplication. Also for a vector space, you have to define some sort of two binary operation, which is addition and kind of also multiplication. And then if the set has those two binary operations with some 8 conditions, we say that this space is a vector space over field F. So what does this mean? And before we talk about this, remember that we called elements of F as scalars? We also call elements of vector space as vectors. So you might heard about the like notation of vectors, right? If maybe you have taken some sort of, I don't know, physics courses or some 이공계 courses, and what they will say is that when you say vector, kind of what you first imagine is actually like a, not this, but you might remember terms like when you say it's vector, it has a direction and power. I'm not sure how to say this in English now. 힘과 방향. When we say vector, we say 힘과 방향을 가지고 있는 걸 vector space, vector라고 한단 말이죠. We call this vector. But actually, that's a very vague and special case. Actually, the rigorous definition of a vector is just an element of a vector space. If you have a vector space, the elements are all going to be vectors. The reason we do this is because this is a very special case because we can make almost everything as a vector space. So we're going to later see the cases where there's a vector space where the elements are functions. In that case, function is going to be vectors, right? In that vector space. But I'm not sure if you can call functions to have a direction and a power. I'm not sure. So this is how it works out. So like the rigorous definition of a vector is actually just an element of vector space. So you have to define vector space first to talk about vectors. So addition and multiplication binary operation is just very similar, especially addition. So basically you add two vectors, and if it still stays inside the vector space, we call that as addition holds. And for multiplication, it's a bit different. We're not multiplying vectors inside. Instead, we're multiplying an element inside V with the scalar A, alpha, where alpha is a field. It's kind of like instead of multiplying two U and V, we're not doing this. We're kind of doing like, this number 4, like number 4 U, like this. It's like scalar multiplication. So we'll multiply scalar to some element in V. And if that stays inside the V, so it's an element of V, we call that scalar multiplication also holds. You don't need to remember all of this. Just remember that this is just good properties. Basically means like, so if F, it's a bit of typo. Not F is a field. We say that V is a vector space if it holds these properties, right? Basically, you don't need to remember all of this. Basically means like associativity, commutativity, identity holds, and there's some nice properties like. So basically, it's like all similar. It's like addition has associative qualities, commutativity holds, and there's also an identity where you just add it, you get the same element, right? And inverse also here. There's inverse elements, and you can also do this with like you can multiply V with beta first, or you can just multiply alpha and beta and then multiply with V, still same values. And there's like identity elements like this. But they all basically mean that the vector space is a very nice space where you can kind of do all these sort of multiplication addition without much trouble thinking about some pathological examples where things go haywire. Okay? So if these 8 qualities hold with the addition and multiplication, we say that V is a vector space. Okay? All right. I'm gonna stop the session with this one. Let me just explain this. So, what is this intuitive understanding of a field in a vector space? Well, I mean, basically, all mathematics, you realize by now that in mathematics, we all start with a set. Like all of the objects we deal with are sets. But we can't do much with just a set. There's nothing that a set tells us, and there's nothing interesting that a property of a set. So what we do is that we need to have some sort of structure or properties of a set to make things more interesting and see how things work out. And this system of a structural property is field and vector space. So basically what we're doing is that there are a lot of ways to define some structure on the set. And field and vector space is just one of the ways to put on some structure or qualities onto the set to make the space more interesting. That's kind of like the intuitive understanding of field and vector space and what we're doing here, okay? Let's just stop here for now, and we'll resume after the lunch break, okay?